So this talk is on Poisson Lie groups and Lie bialgebras, and I know many of you are here for the summer school, for the school, and in which Edinghoff gave 4 lectures on this subject. And if you recall that he gave the definition and Poisson Lie groups, Lie bialgebras, and how to construct Lie bialgebras from Mounting triples, and then he also covered the standard Poisson Lie group structure on the semisimple Lie algebra, Lie group. Okay, so this talk can be regarded as a sort of follow-up on his lectures. I'm also very happy that Eckhart this morning gave some reviewed the definition of Poisson Lie groups and actions of Poisson Lie groups. So, my first goal for this talk is to explain a class of examples of Poisson structures which have Poisson Lie group actions. And I like to try to say that there are something very interesting you can say about them. But I actually have a second goal. So as you all know, that the theory of Poisson Lie groups and Lie bialgebras was discovered or started about 30 years ago by the Russian school like Grunfeld and Semyonov-Tienshansky and Alexeyev-Riemann and Reshtikin and so on. So the theory has been there for 30-some years. So recently so this is joint work with my former student, Victor Mouquin, who is also here in the audience. So we were looking at a particular example of Poisson structures. Then we realized that the theory that has been existing was not enough for us to understand this Poisson structure. So we had to go back to the theory and try to develop it a bit more. And so we discovered something, or maybe I should say maybe rediscover something. So my second goal for this talk is to sort of appeal to the audience. I mean, many of you actually know the literature better than I do. Maybe you can actually see perhaps some of this new constructions is already exists in the literature, or maybe some trace of it. But also, perhaps this can also be generalized to other like quasi-Poisson structures or Dirac to quasi-Poisson geometry or Dirac geometry or Courant algebroids. Okay, so that'll be my second goal for this talk. So first of all, I just to make it sort of self-contained, I will quickly recall the definition of Poisson Lie group. So a Poisson Lie group is a pair G and pi, where G is pi G. So G is a Lie group. So G is a Lie group, and pi G is a multiplicative Poisson structure in the sense that the group multiplication is a Poisson map. So in particular, so this is G1, G2 goes to G1, G2 is Poisson. Now, in particular, this means that the Poisson structure may not be may not be invariant under left translation. So, then the Poisson action by a Poisson Lie group is an action. Is a Lie group action which is also a Poisson map. So it's a Lie group action on the Poisson manifold is an action which is also Poisson. A Poisson map. So in particular, the Poisson structure on Y is not necessarily invariant under the group action. And then we have this infinitesimal version of this. So you have a Lie bialgebra for a Poisson Lie group. So starting from a Poisson Lie group, you get the Lie bialgebra. So the Lie algebra of G, of the group G, let's call it German G. And then the cocycle, so what's a Lie bialgebra? Is a Lie algebra together with a cocycle, I just call it this. This by definition is a map. So it's the linearization of the Poisson structure at the identity, which is a map, which is a linear map, which is a linear map from the G to the wedge 2 of G. Now we all know that the linear, because the Poisson structure vanishes at the identity, so you linearize it. If you dualize this is a Lie bracket on the dual of the Lie algebra. So a Lie bialgebra is a pair. It's a Lie algebra together with this cocycle. If you regard if you look at the dual of the cocycle, that's a Lie algebra structure on G star, and there's a compatibility condition between these two. So here there are two conditions: is the dual satisfies so the dual map is a Lie bracket. So this is the Lie bracket. And then there's a compatibility. So you regard the Lie bialgebra as a pair of Lie algebra, or as a Lie algebra structure on the vector space and a Lie algebra structure on the dual vector space. The compatibility is in terms of expressed as a cocycle condition. Okay, so that's what a Lie bialgebra is, and every Lie group, Poisson Lie group, gives rise to a Lie bialgebra. And then with some connectedness and simply connectedness condition, you can integrate a Lie bialgebra to a multiplicative Poisson structure on a group, making it into a Poisson Lie group. So there's this correspondence between Poisson Lie groups and Lie bialgebras. And then what about an action? So the infinitesimal version of a Poisson action is so a Poisson action of a Lie bialgebra is a Lie algebra action. So when I talk about Lie algebra action, I will be making a difference between the left Lie algebra action and the right Lie algebra action on the manifold. For left Lie algebra action, I mean a Lie algebra anti-homomorphism. Okay. For right Lie algebra action, I mean a Lie algebra homomorphism. So this would be, for example, this would be a left Poisson action of a Lie bialgebra is a Lie algebra anti-homomorphism sigma from G. So I should say a left Poisson action of a Lie bialgebra on a Poisson manifold. Okay, it's a Lie algebra anti-homomorphism. So therefore, that's what I mean by left action, such that this means the space of vector fields on Y, such that if you take the Lie derivative of your Poisson structure on here, then this is not equal to 0. If this were equal to 0, then it will be acting by symmetry, by isomorphisms, but this is not. So you have sigma acting on delta of x. So delta of x is an element in the wedge 2 of G. So you apply sigma to it, you get a bivector field on Y. So this is the condition for Lie bialgebra action. And then there's a correspondence between it's a theorem that proved by Alan Weinstein some 30 years ago that if you have a Poisson action, if the Poisson Lie group is connected, then if you have a Lie group action of your Poisson Lie group, then you look at the corresponding infinitesimal Lie algebra action, then this is a Poisson action if and only if it's a Poisson action by the Lie bialgebra. So this is all standard. Okay. So now how do we? So this is my very quick review of Poisson Lie groups and Lie bialgebras. So now I want to try to convince you that there's a very rich world of Poisson Lie groups and Lie bialgebras. So let me just say Lie bialgebras. So in constructing these Poisson structures, I only need infinitesimal actions. So I'll just so the rich world of Lie bialgebras. So let's again recall this is something that was again covered in Eddinghoff's course and also in Eckhart's talk early this morning. So you construct Lie bialgebra by Manin triples. So we recall that a Manin triple. So a Manin triple. So given a Manin triple. So recall what's a Manning triple. So I denote, for me, I denote the Manning triple in this way. Well, Eckhart put this, so this is the bilinear form. So D is a Lie algebra, and this is an invariant metric. So meaning that it's invariant, symmetric, and non-degenerate bilinear form on the Lie algebra, and such a thing is called a quadratic Lie algebra. Okay. And so this is, so I put that in here, and then I also have a quadratic Lie algebra, and then G and G star, where D, this is a quadratic Lie algebra. So once again, this means that you have a Lie algebra, you have a symmetric, non-degenerate, invariant bilinear form. And then G and G star, so D is written as G plus G star as a vector space. And then G and G star are both Lagrangian. Lagrangian sub-Lie algebras. Lie subalgebras. So I require this to be Lie subalgebras. Lagrangian means they are maximal isotropic. And I would also call this guy here, I also refer to this as a Lagrangian splitting. Okay, so a Manning triple is just such a thing. What I like to emphasize is that I could have the same quadratic Lie algebra, I could have different Lagrangian splittings. Okay, the same, so I'll mention that a bit later. The same quadratic Lie algebra could have lots of Lagrangian splittings. Okay, so given the Manning triple, so here what these two are identified, because they are maximal isotropic, so the pairing between these two is non-degenerate, so they are naturally identified as the dual spaces of each other. So therefore, so the Lie bracket, so the dual of the Lie bracket wedge to G star to G star. So this dual of the Lie bracket on G star is delta G, which is a map from here to here. Okay, and the same thing, the dual of the Lie bracket on G gives a map from G star to wedge to G star. Okay, and then this way then the statement is that this way I get a pair of Lie bialgebras. So G and delta of G and G star delta G star are Lie bialgebras. Okay, so this is a very simple construction, and these are called dual. This is a dual pair of Lie bialgebras. Okay, so every time you have a Manning triple, you get a Lie bialgebra structure on either of these two, on either one of the two vectors, and they are dual to each other in the sense that the bracket of this bracket here dual is this guy. This is so that's a dual pair of Lie bialgebra. But not only that, you actually get a third Lie bialgebra. Moreover, also have the Lie algebra. Have the Lie bialgebra. You get a third one, which is called the Drinfeld double, which I denoted by this, D delta D, where D is this big Lie algebra. Yeah, you have triple of Lie algebras here. So the big Lie algebra also is made into a Lie bialgebra by taking this, so delta D. So every element in there, because it's a sum, so every element here in D is a sum of something in G and something in G star. So this is in G, this one is in G star. So you simply take delta G on X minus delta G star on C. Okay, so then this is called the double. So this is called the Drinfeld double. Of this one or the other one. So every time you have a Martin triple, you actually get 3 Lie bialgebras. You get 1 Lie bialgebra, you get its dual, and you get their double. Now, how do you get Poisson Lie groups? If D is any connected Lie group with Lie algebra D, I get then define pi D I can define a bivector field on D. Now this bivector field on D is going to be, so its value at an element is the left translation, so let me use the right translation of something I call lambda subscript GG star minus left translate lambda GG star. So this is a bivector field on D, where lambda GG star, so it's 1/2 summation Ci wedge Xi, where I from 1 to M is, then this is, so I'll explain, then D pi D is a Poisson Lie group. So this means it's multiplicative and it's a Poisson structure with Lie bialgebra the double. So now here, this is a basis. So this guy is a basis for G. And this is the dual basis for G star. Okay. So you see, this construction is very straightforward. It's not only this, you get a Poisson Lie group that integrates the double Lie bialgebra, but moreover, if G and G star are the connected Lie subgroups, integrating, so the Lie algebra of G is G, and the Lie algebra of G star is G star. Then you also get, so what you do is that then you prove that G and G star are actually Poisson submanifolds with respect to this pi D. So therefore, then you get a pair of, so by this, I mean, it's the restriction of pi D restricted to G. So then for G star, you take negative pi D restricted to G star. Okay, then these are Poisson Lie groups. With Lie bialgebra G delta G and G star delta G star. Yeah, so this construction is very simple. You probably heard that in Eddinghoff's talk, if you have a Lie bialgebra, if you try to integrate it to a Poisson Lie group, you have to assume the Lie, if you want to get a theorem that works in all the cases, you have to assume the group is simply connected, then you have to do some kind of integration, integrating some vector fields, and it's like integrate. Anyway, you have to do some integration. But here I'm giving you a situation where you basically don't have to do anything. Once you have a Lie bialgebra, a Martin triple, this is all you need to start with. You have a Martin triple, you get 3 Lie bialgebras, one and the dual and their double, and then you can automatically get a multiplicative Poisson structure on the double by using this, translating the R matrix. This guy is called the R matrix. And then you also get a 3 Lie Poisson Lie groups. Yeah. Okay. This is because this guy is the so-called co-boundary. For co-boundary, you can just write down the Poisson structure right away without needing any integration. All right, so this is a very general scheme. So just remember that every time you have a Martin triple, you get Poisson Lie groups and you get 3 Poisson Lie groups. And then I would actually again then concentrate on an example of this. If G, if you have what's called a quadratic Lie algebra, if this is a quadratic Lie algebra, so once again by this I mean a Lie algebra with an invariant metric. Let G plus G be the direct sum. So let direct sum or direct product Lie algebra. And you define a bilinear form on the sum. This is what Eckhart called G and G bar. So I somehow am using this. So given by, so you have an x1, x2, y1, y2. So you define this to be x1, x2 minus y1, y2. So this is what he called G bar. So this is using the given bilinear form on G, and this is the one. Sorry. Okay, so Eckhart denotes this by that. Okay, all right. So given this, you have this. Now this guy said, note that then G diagonal sitting inside this double, let's call it XX, is Lagrangian. It's a Lagrangian subalgebra. Okay, so therefore any complement of the double would make this into a Martin triple. So any Lagrangian complement by that I want it to be a Lie subalgebra. So it's a complement is Lagrangian, also a Lie subalgebra. G prime of G delta in here would give you a Martin triple. And then out of that Martin triple, then you get 3 Lie bialgebras and 3 Poisson Lie groups. Yeah? Gives the Martin triple. So you have G plus G with this bilinear form. So this is a quadratic Lie algebra. You have the G diagonal, you have this G prime. So the a Lie bialgebra structure on G obtained this way. So G is now identified with the G diagonal. Obtained this way is called, is said to be, this is special, not only bialgebra structures are obtained this way, but if it is obtained this way, it's said to be factorizable. Okay. All right. Factorizable mainly because the double is a product. So in particular, if you consider if G is complex and simple, so as a further example of this example, so G is complex or real, doesn't matter. Actually complex and simple, and then this I take this to be the killing form, and then I take fix any triangular, so-called triangular decomposition. So you have so the lower triangular plus cartan plus upper triangular. So then I can take G prime to be something like this. This is x plus x0 minus x0 plus x minus, where x plus minus belongs to n plus minus, and x0 belongs to the cartan. And this is the Lagrangian complement of the G diagonal. And then this is a Lagrangian complement to the G diagonal, and then the induced Lie bialgebra structure on G is called the standard one, the so-called standard Lie bialgebra structure on G. Okay, so this is going to be my running example. This is the example that I'll be referring to most of the time. But then the other factorizable Poisson Lie bialgebra structures on the simple G is all classified by Belavin-Drinfeld. So when I say the rich world of Lie bialgebras, okay, now typically I'm interested in the case when your underlying Lie bialgebra is semisimple. It can be real semisimple or complex semisimple. So let me just recall without writing down much that for factorizable, if G is complex simple, and then the factorizable Lie bialgebra structures are classified by Belavin-Drinfeld. And then you can also consider the case where your Lie algebra is real. It's a real form of a complex simple Lie algebra. And then you can also ask for Lie bialgebra structures on there. And that has to be, there also has been a lot of work on that. In particular, let me just mention that, so there's, when G is real form, so like SLNR or SUPQ, and then there's this work by a number of people. Maybe I don't think I have the time to list all of these people. So this you can also study, but the classification is rather complicated. So you can also ask for a Lie bialgebra structure on here whose complexification is this guy here. Yeah? So you can fix the complexification. In other words, you fix a Lie bialgebra structure on here, you look for all possible real forms of that complex Lie bialgebra, and then so that, for example, if you take the standard one, you'll ask for, and you also fix the real form. You ask how many Lie bialgebra structures there are on here whose complexification is the given one, and then that's also very interesting. So for example, if you take G to be E8, the complex E8, and G0 is the split real form of G, and then there are something like 135 Lie bialgebra structures. So this is up to isomorphism. You have to define what you mean by isomorphism, but up to conjugation, Lie bialgebra structures on G0 whose complexification is the standard one. Delta is the standard one. So then this here is also, this is a very interesting story. So this has to do with, if you look at the group level, you have this integrates to a real semisimple group, this integrates to a complex semisimple group. And then this, what I'm talking about here are these open G0 orbits on the flat variety of this complex Lie algebra. And then how did I get this number 135? Because we have you can prove that such Lie bialgebra structures corresponds to those open orbits. And then there are these people who in Lie theory, they have this atlas on Lie groups where they are doing the Cauchy-Nanostic polynomials and so on, where they have a program called KGB, which tells you how many such orbits there are. That's a very small part of their program. But you use their program, you can see how many such things there are. So there's lots of interesting geometry in here. So what is my message here is that even if you start with your favorite Lie algebra, fix your favorite Lie algebra, already there are many different Lie bialgebra structures on that same Lie algebra. Okay? So for the complex semisimple case, you have the Belavin-Drinfeld type. Here I just give the standard one. If it's real, then you also have many, very interesting. There's also lots of interesting geometry behind it. But not only these guys here themselves are Poisson Lie groups, you also have their duals. Yeah? Their dual Poisson Lie groups are typically not semisimple anymore. They are like solvable. Or you also have their doubles. Yeah? So this way, then you can continue actually. You have the double, then you have the dual of the double. And then you can do double, double again. So there are lots of, so starting from this, you can see there are lots of Poisson, examples of Poisson Lie groups and the algebras. And not only that, they also have interesting Poisson Lie subgroups, which are Lie subalgebras. So in this example, so for the G pi standard, so this one here, I meant, by that I mean the one that integrates this one, okay? For this, the Borel, where the Lie algebra of this B is the H plus n minus, is a Poisson Lie subgroup. For those of you who know this subject, the G is almost the double of this Poisson Lie subgroup. So anyway, so not only that the semisimple ones have nice, have interesting Lie bialgebra Poisson Lie group structures, but they also have interesting Poisson subgroups. Okay, so far I have only tried to say that there's a rich world of Poisson Lie groups and Lie bialgebras, and then you would naturally ask, are there lots of examples of Poisson structures with Poisson actions by all of these Lie bialgebras and Lie group, Poisson Lie groups? And the answer is yes. So this is what I mean by the rich world of Poisson manifolds with Poisson actions. Let me just call this with Lie bialgebra symmetry. Okay. Oh no, I still call it, sorry. Poisson actions of Lie bialgebras. Of course, you can consider these groups themselves as the action will be left translation, and these are all interesting examples, but then, of course, this should not be the only ones. So here, I would like to give you one construction of such things, and I have believed for a long time that at least all the examples that I know, they all fall into this one class. And then the point is that then we recently ran into some other examples where we couldn't fit it into this class. So then we struggled it for a while, and then we realized that again it actually fits into this class. But in order to realize that, we have to introduce something new. So that's what I meant by sort of discovery or new discovery. So what is this one construction? So this construction is actually more or less already mentioned in David Lee Bland's summer school courses, and also in Eckhart's course, and then this all the. So here, this is one construction. So given a quadratic Lie algebra, D, so I call a Lie algebra action sigma of D on the manifold Y is, we say it is said to be admissible. I don't know, it's just a short way of talking about things. It's admissible if the stabilizer at every point is coisotropic. This is with respect to the bilinear form. Okay? And then the construction is the following. So given the Lie bialgebra, so then it's the lemma. This was written in a paper by myself and Milan Yakimov. But then later on, it was put into the framework of Courant algebroid by David Lee Bland and Meyer Rankin. So here's the construction that So if you have a Lie-Martin triple, and you have a sigma, which is an admissible action of the double of the big Lie algebra of D. When I say admissible, I have to refer to the bilinear form, so I call it so it's the admissible action of the quadratic Lie algebra. Then you get a Poisson. So pi y by definition is defined to be you just sigma wedge sigma of what I call the lambda g star. This is the R matrix, so which is by definition is 1/2 summation sigma ci wedge sigma xi. Remember, since you have a Lie algebra action, this is a vector field. This is a basis for G. This is a basis for G star. So they're dual bases, and then sigma of that is a vector field. That's another vector field. You wedge two vector fields. It's a bivector field. Take the sum, and then this is Poisson. And sigma is a Poisson action of the double Lie bialgebra. On this Poisson manifold. So this is one construction, and this construction is very simple and straightforward. Okay. And my point is that all the Poisson structures I know are of this type. And those Poisson structures I know that are related to the Poisson Lie groups, and they are all of this type. Now I want to get a little bit sort of philosophical about this. First of all, so let's look at this definition of this Poisson structure again. In general, when you have a Poisson manifold, you have a Poisson structure, you sort of try to write it down locally what it looks like. But what happens here is that this Poisson structure is very special because it's a sum of wedges of globally defined vector fields. Yeah? So that's one feature about it. And secondly, because it comes from the Lie algebra action. So because of this, you can actually study all. I mean, at least philosophically, it's easy to believe that all the Poisson geometrical properties of this Poisson structure can or should be understood in terms of, in Lie algebra terms. Okay, so that's really the whole idea. So for example, you want to know what the symplectic leaves are. You want to know what's the Poisson cohomology. You want to know about the symplectic groupoids for this kind of Poisson structures. Okay, so so for example, the symplectic leaves, or rather the rank of the symplectic leaves, the ranks of the symplectic structure can be computed by dimension of intersections of these subalgebras. Okay, for this you have to believe me. There is a theory. So Eckhart mentioned a theory about Drinfeld's theory about Poisson homogeneous spaces, and Yakimov and I developed a bit further in our paper on something about this type of Poisson structures. You just have to believe me that for this type of Poisson structures, because it's defined by Lie algebra action, so everything is interpreted in terms of, everything can be expressed in terms of Lie algebras. So leaves will be intersections, can be intersections of orbits of subgroups of D. Okay. This, in particular, the rank of the Poisson the dimension of the symplectic leaves can be computed in terms of dimension of intersections of subalgebras. Poisson cohomology can be expressed in terms of relative Lie bialgebra cohomology. This is sort of translating from one language to the other, okay? So, and then groupoids. Symplectic groupoids will be transformation groupoids. Okay, so this is the flaw. This is the idea behind the. This is the reason why this type of this class of Poisson structures is easy to understand. In term, I mean, now of course you still have to compute relative Lie algebra homology. You still have to look at all of that, but it's translated into Lie algebra language. Okay, so that's the whole idea. So then I want to explain. Then what are examples of this? Examples that fall into this class. I won't go into details. Okay, you can. My background is always a complex semisimple Lie algebra or a real semisimple Lie algebra. So then you can talk about conjugacy classes. Conjugacy classes all carry some Poisson structures whose leaves are very interesting. So I won't be able to explain conjugacy classes, flag varieties, semisimple symmetric spaces, and their wonderful compactifications. And so in particular, like Eckhart mentioned, that the variety of Lagrangian subalgebras. So these are interesting varieties that you can, the Grassmannian of all Lagrangian subalgebra. So all of this will fall into this. I won't give details on this. So they all belong to this. What I'm saying is that all of these interesting varieties in Lie theory, they carry naturally defined Poisson structures out of this construction, and they can be expressed. They can be studied using the original Lie algebra. Okay. So now I want to explain this class that Victor and I ran into recently, and then we won't be able to. For that one, we are actually not able to, at the beginning, not able to understand that Poisson structure in this. But then later on, we realized we can. But then in order to do that, we need some new ingredients. So what is this example of Poisson structures? Now a new class. So let me give you another example. A class of examples. So the examples is this. So let G be any Poisson Lie group. And then let Q1, Q2, Qn be n closed Poisson Lie subgroups. And then form the quotient space. So the quotient space Y is this. So I denote it in this way. So this is the quotient of Q1, Qn action on n copies of G by so the action is G1, Q1, Q1 inverse, G2, Q2, Q2 inverse, G3, Q3, and so on. So here you have Gn, here you have Qn minus 1 inverse, here you have Qn. Okay, if you haven't seen this action, it's maybe a bit, takes a little time to take it in, but this is a free action, okay, of this group acting on here. And then the fact is easy, it's an easy fact that the product Poisson structure of the product, the direct product Poisson structure on G. So the Poisson structure on G is pi G, projects to a well-defined Poisson structure on this Y. Okay, this is an easy thing to prove. And this is what we refer to this as the quotient Poisson structure. And it's this one that we are particularly interested in this example. So we call Fn, which by definition is G, B, B, G mod B, where G is semisimple with the standard multiplicative Poisson structure that I talked about earlier on, and B is the Borel that comes into the definition of the standard multiplicative Poisson structure on G. Okay. Now I can spend a lot of time explaining why. So at the end I'll explain what we can say about this particular case. So this is the one that we're interested in. The problem with this Poisson structure is that I don't see much symmetry anymore. Even as a manifold, if you look at the way that is defined, because of those intermediate quotients and all of this, all you can see is that the group G still acts on the first factor. Okay, but then other than that, I don't see much symmetry anymore. Whereas this kind of construction has lots of symmetry in there. Okay, so I don't see that. But then, so for a while, we were inventing all sorts of other things to study this Poisson structure. But then later on, then there's a key observation, which is very simple. And so then the observation is that we have actually, but this is a very simple thing. We have a diffeomorphism from this Y to actually products is actually, as a manifold, is actually products of these quotient spaces. So how do you do it? Here you have G1, G2, and this is the class defining Y. This just goes to G1, Q1. And then if you multiply this two, you see this. If you multiply this two, you see the middle thing get canceled. So you get G1, G2, and that's a well-defined element in this quotient, and then you multiply them together. Okay, so this is a well-defined map. It's a diffeomorphism of manifolds. So at least suddenly, if I look at it as a quotient like this, I don't see any symmetry even as a manifold. But if I sort of unwrap it in this way, I see at least the G X on here, G X on here, so G to the n, and now X on here. So that's the first observation. Actually, there is quite some, it's a big symmetry on this manifold. Secondly, because the multiplicativity of my original Poisson structure, if you project to each factor, then you are projecting to each factor here. Because the Poisson structure is multiplicative, so this multiplication is always a Poisson map. So, so if you consider I of pi y as a Poisson structure, now on the product, so now is a Poisson structure on the product. So now you're looking at a Poisson structure on the product manifold whose projection to each factor is a Poisson map. Now that's because if you project to each factor, that's because the original thing is multiplicative. So therefore, this raises two questions. The first question is, as a manifold, I see the symmetry, but how about the Poisson structure? Do I have Poisson-Lie group symmetry? The second one is, how do I understand this Poisson structure on the product manifold? Okay, now the answer, so the final answer is that indeed, the answer is yes, so we are trying to understand two things, the Poisson symmetry of this guy, and secondly, how is this how does it differ from the product Poisson structure? So let me just quickly give you the answer. So the answer is that I have this guy does have fall into this construction, but I have to invent a much bigger Manin triple, and so this is my first thing. So this is what I call something that we realized, but I'd like to ask some of you whether you have seen this before. But then I actually talked to David Leblanc, and he reminded me that this construction, for the case when G is factorizable, is already in the paper of, there's something that is in the paper of Falk-Rossley on this modular space of flat connections, where he talks about the polyuble of Lie bialgebra. So, but unfortunately, I cannot check whether theirs is the same as ours, because theirs are given by pictures. I don't know whether, at this point, I don't know whether it's the same. So before I know for sure that they are the same, I'm going to give this a different notation, different name. So I call this a prolongation. Is this the same as the polyuble? I don't know. So polyuble of Lie bialgebras. So basically what it says, if this is a Lie bialgebra, you can construct with dual and double. So given this, you can construct so let Dn be n copies of D with the bilinear form is so I just write it as this. Alternating sums. Okay, so alternating sum of the original one. And then this guy have a Manin triple. A Lagrangian splitting. Dn, which is equal to Gn plus Gn star. So then where the Gn, depending on whether n is even or odd, d diagonal, and Gn star is G star. So let me just G and Gn star. So depending on whether n is even or odd. Okay, so this is n even, this is n odd. And then the theorem is that this Poisson structure is defined by this Manin triple with what is the admissible action. In fact, the double Lie algebra actually acts on here, on this quotient. Okay, the double Lie, here you only see the G action here. But in fact, the dressing action also descends to here. So not only have the left translation by G, you also have the dressing action. So each copy has a D action. So therefore, the direct product action of this on here is an admissible action for the Lie bialgebra. Now you have a Lagrangian splitting, so you push the R matrix to here, you get a Poisson structure. So as a result, this Poisson structure has a large Poisson symmetry by this guy. So I call this guy the nth prolongation. Maybe later on it should be called n-ubel of G. It's a Lie bialgebra, and its dimension is n times the dimension of G. For n equals 1 is G itself, for n equals 2 is the double, n equals 3 you want to call it the triple, and the quadruple, and so on and so on. So the statement is that this guy here, sorry, I don't have time to write down the theorem. The statement is that this guy has the Poisson symmetry by this large, big Lie bialgebra. And I don't have time to talk about the mixed product, but the other assertion is that as a product, as a Poisson structure on the product manifold is a mixed product, and the mixed product corresponds to fusion product in the case of quasi-factorizable Lie bialgebra. Sorry, so that takes too long, so I don't have time to do that. But I do want to show you now, after the realization of, so remember I said that we are interested in this example. This is our motivating example. So after we realize this, then we have to develop a bit further on the theory that Yakimov and I did. Hey, why doesn't this work? Okay. Okay, so I want to show you what's the application. Oh, well. The application of this is that we are able to understand, there's a lot of things that one can say then. You develop the general theory a bit further than you apply to this example. And then we are able to understand what the torus orbits of symplectic leaves are. We are able to decompose this into pieces. each piece is, so this whole thing now is decomposed. For one thing, we can describe the torus orbit of symplectic leaves on here. There are only finitely many. That's the key point. And those T leaves are described by Wald group elements. That's the first statement. Second statement is that this whole thing is decomposed into finite number of pieces. Each piece is a copy of C to some number K. And on each copy, you have a natural coordinates. You can compute the Poisson structure very explicitly on every piece. Okay, so this whole thing is written as a disjoint union of pieces. And then each piece depends on some n alpha, where alpha is some index. And on each one, we have natural coordinates, and you can compute what the Poisson structure looks like. And therefore, you can compute the so-called T-Pfaffian. You can understand the lots of things. Okay, sorry, I don't have time to explain. So all of this is to develop that. Yeah. So yeah, I'll just show you the formula. So this is a piece in F20. I just randomly choose the numbers. As long as, this is for the group G2. As long as 23 is bigger than 9, I think this will work. So this, you have this example. So we can just show you what the Poisson breadth. So if you compute in pieces. So this is between 1 and 9, but so somehow 9 is special. And then 2 and 3 and 2 and 9. And then you get this, 4 and 9. And then so the Poisson structure looks like this. And then it's fun. By the way, so this was done by a former student of mine, Balash. And then if you try to compute Jacobi, you want to make sure that you did not cheat. So you compute the Jacobi. So this is 100 some terms for this, and then 100 some terms for this, and you add them together, you do get 0. So yeah, okay. Yeah, sorry, I still have like 1/2 of my talk I cannot explain. At the level of Gn, T. Where's D? Oh, here. Ah. Oh. Yeah, there is. Yes, that's the simple answer. Yes. No, but the simplest answer just because the Poisson structure is multiplicative. That's all. But then you're asking, maybe you can say you can enhance that statement, and then so these partial projections would also have symmetry by the Dn. I forgot to say one thing. All the motivation for why do we care so much about this one is on these T leaves, we hope to get cluster algebra structures. So all the explicit calculations in coordinates would allow us at least to check those log canonical of those coordinates which are log canonical with respect to these brackets. These brackets are not log canonical, but you can write down in terms of representations. You can write down functions which are log canonical, and then those will be the initial seeds for doing cluster algebras and so on. So that's the one of the motivations for studying this one. But in any case, this is very explicit. This is something you can really get your hands on. You can do lots of things about this. Yeah, thank you.